My name is Joaquin. Alex is my advisor, and I just added there so you know that you are in the right presentation. The former title of the document you received was Application-Driven Learning for Demand and Reserve Forecasting, a Bilevel Optimization Approach. And we talked a lot with Tito Amendi-Melo and Pancho Munoz in this work. So there's some suggestions of them over there. I'd like to thank them in advance for collaborating for what we've done. So the first thing I'd like to say is that the main paradigm of this work is decision under uncertainty. This is a very broad subject, and many of us use that a lot in very different fields with very different techniques. But the broad scheme is that you have a first state decision, which could be a decision whether to invest on a stock market or to dispatch a thermal plant or a hydro plant, depending whether you want to save water or not. A second step, uncertainty is observed, and then, well, market prices might go up and down, and inflows might show up for a thermal or hydro operation, and that might affect your first state decision. And now you have a second state decision in which you have the chance to adapt to this new observed uncertainty, which could be seen as a reallocation of portfolios, shutting down of thermal plants by using the new water, or even spilling the water that you didn't account for. Something very interesting about this paradigm is that in many times, the costs of your decisions are very asymmetric. So I brought here two examples. The first example is this parkour guy over here. It's very interesting because he's jumping from one roof to the other, and his cost function for whatever he's doing is extremely asymmetric, because if he doesn't jump with enough height or with enough strength, he will fall, and he might even get serious injuries or even death. Otherwise, if he jumps a little bit too further, well, he just lost a bit of extra energy. So sometimes it's better to staying alive and just wasting a little bit of energy. A second example, which is present in some books about forecasting, there is Nate Silver's book. This is one of the examples over there, is weather forecasts. Weather forecasts are typically biased. And the reason for that, people have been looking into that. And the thing is, the user of the weather forecasts, they have very asymmetric opinion on what happens in each of the cases of the weather forecasts. So if the forecast is a lot of rain and it turns out to be sunny, well, whatever was looking at those forecasts will be just like, okay, I thought it was going to rain, but it was sunny. That's fine for me. If it's a case of bringing the umbrella to work, he'll just put the umbrella in the backpack. Okay, it was just a little bit of extra weight in my backpack. That's fine. The opposite is much worse, because if the forecast is a sunny day, but if it rains, then you might have forgotten your umbrella, so you get totally wet, and that's not good at all. Or you might even went to Búzios like Alex, and having a lot of rainy days in Búzios is also not the best thing you could have for. So what happens is the providers of forecasts, they do biased forecasting.
Joaquim, I have a question. Who's the source of the example again was from?
Was Nate Silver's book, is The Signal and the Noise. It's one of the chapters in the book. It's about weather forecasting.
Not Silver as in David.
Nate Silver. No, not David Silver. It's Nate Silver.
Okay.
The guy from that website 538 from forecasting elections. He has this.
Okay. Okay.
He does a bunch of forecasting and a bunch of things, and I can send you a reference of the book later.
No, I was just wondering if there's a reinforcement learning guy who was in.
Oh, I see.
And he jumped to DeepMind or something. I was wondering if he had a book, but thanks.
So okay, what do we do in this world where where everything might be asymmetric. So the first thing that we thought was there is this paper from Rockefeller where he talks a lot about asymmetry on costs and doing forecasting that is very tied to the asymmetry of the problem. So he proposes doing quantile regressions for forecasting some stocks when his problem is some risk-averse portfolio allocation. But the thing with that is that this is kind of an empirical approach that doesn't take the actual cost function of the problem into account, because you're just like, since I'm doing something that has this var constraints, maybe I have to bias my forecast, but you don't know exactly how much. You just know that you have to bias a little bit. So we're calling this some sort of an empirical approach. So the second option is what we've been calling the application-driven approach, which also splits in possibly two lines of work. One of them has a lot to do with a recent paper from Bert Simas, which is about prescriptions and predictions. And the idea is, instead of improving a lot your predictions, maybe what you want to do is improve your prescriptions by adding extra information in the prescriptions problem instead of working a lot in the predictions. In this work, in some sense, the predictions still come from outside, but you are biasing the prescriptions by taking extra information into account. The second work, the second line of research that has been having some attention recently has a different approach, which is doing both the prediction and the prescription the same problem, which amounts to actually creating a new prediction. But in this new prediction, we will have the cost function, which is exactly the cost function of the actual problem. So the first time it's been done, it was in the late 90s by Joshua Bengio, one of the guys from machine learning. He's been advisor of Geoffrey Hinton, I think. And his idea was to train a neural network with the cost function of financial loss, because his problem was a financial problem. And he used this financial loss cost function instead of a classical least squares to produce a forecast that is correctly biased toward his applications. More recently, this approach has been having some additional attention. So besides the financial work based on neural nets by Bengio, we have seen this work by Priya Donti and Zico Coulter and one of his students who is in Facebook right now, called test-based learning. This was a paper on NIPS. And in this paper, they kind of use the same idea of training their forecast based on the application cost function. And they use a gradient descent approach with some automatic differentiation of quadratic programs. The third work that is actually very recent also is this one that is still in archives called Smart, Predict, and Optimize. I think it's submitted to Management Science by these two guys, El Maktoub and Griga. And what they do is that, again, they consider the actual loss function of their problem to estimate uncertainty. And what they do is that they do relaxation and convexification of the nonlinear problem, and then use the stochastic gradient descent on linear programmings to solve that problem. And one highlight is that the only thing that they are estimating is uncertainty in the objective function. The fourth work was like from December 2020, is a work from Morales and Pineda, and they've been working on bilevel optimization to solve these problems where the application cost function is the main cost function of the problem. And they've been solving those problems using Fortuny-Amat reformulations and nonlinear programming of the entire problem. So there's no decomposition there. It's just straightforward techniques of solving KKT reformulations of bilevel optimization problems. A little bit on load forecast and reserve size, because, well, our idea is to use the cost function of the real problem to direct our forecast. But also, what we want to do is that we want to solve a real problem, which is the problem of forecasting load and sizing reserves in power systems. So, well, as we all know, loads and renewables, they are one of the key sources of uncertainty in power system, and the systems must be ready to withstand the changes in the power systems, in this case, mostly due to uncertainty on load and renewables, because you can always think of renewables as some change of loads, not always, but in many situations. One of the classic solutions for that, it dates back from the 60s, is using reserves. And that's what most of the power systems, I say that even all the power systems, I'm not sure any power systems that not account for reserves. Maybe a few do, but it's a pretty standard practice to use reserves. And these reserves would be margins on the generators on which they can operate, and the system can adapt to the new realization of the uncertainties. And more recently, there's been a lot of work on doing dynamic reserves, because all these loads and renewables, we can exploit their pattern as time series, and we can try to have reserves varying time instead of a single predefined reserve for the whole month, for instance. The other main approach to withstanding uncertainty and responding to that is using stochastic optimization. And that would be called a endogenous approach. It's a very interesting approach, and it's a very complete approach, and theoretically very sound. However, there are a few issues that have been pointed out by some papers on using stochastic optimization, and there are a few challenges for power systems to adopt stochastic optimizations. And some of the main challenges is proper uncertainty modeling, computational performance, and even market design, because sometimes some players of the market might not agree with some of the new ideas, although they might be sound and theoretically correct. So now I want to talk a little bit again in the generic framework and what people actually do. So I'm bringing back the initial concepts of this presentation, and this chart here will follow us along the presentation. So what people usually do is that they train a model for forecasting. So they have data for that, could be historical data or future data. They train a model that will, usually those models are parametric, although there are a few models that are non-parametric that people use. But with a model and with data, you can produce a forecast. Once you have a forecast, you can plan your policy, so you can plan for the next day. And that's what many power systems do once they decided what's their forecast or what's their reserve sizing, either dynamic or not. And once they have a plan, they have now, okay, now we want to do this. We want to follow these set points for generators, or we want to follow these commitment issues or things like that. However, after that, the uncertainty is realized, and the system has to adapt. And once the system has to adapt, the system adapts, and you suffer a cost function for that. So you have a cost of that adaptation and the cost that you incurred of your initial decisions. So this is a classical model, and it's very, when you're looking to that picture, it's like you really want to bring that last arrow over there and plug that on training again, so that you have a feedback loop and everything agrees with each other again. And that's the main idea of this work. So now we want to close this loop, and we want to do the whole thing at the same time. So in this new idea, the model will be trained with the actual cost function of the problem, taking into account both the planning step and the final evaluation step. And well, the figure is nice, but we have to put that in more concrete terms. So in order to formulate whatever is happening in that figure, we wrote that bilevel formulation over there. And I want to explain that bit by looking at the figure. So orange boxes now are marking the forecast step in both models. So there is this constraint here in the model saying what will be your forecast given the parameters that you're optimizing for, in your historical data, for instance. So you have a forecast for a bunch of observations. After that, you bring that forecast to an optimization problem, this argmin over here. And during this optimization problem, what you're doing is that you're planning your system for that specific forecast. Okay, once you have that plan, you have your x variable, which is the representation of your plan. And the final step is you evaluate that plan that depends on the uncertainty. So you see that x depends on psi hat, but that is evaluated against the real historical data of the uncertainty. So you see that psi in the second part of the objective function is the real psi from, for instance, your historical data. So everything is evaluated in the actual cost function of the problem. And training the thing, we are minimizing theta, and we are minimizing the entire thing altogether, which is a bilevel optimization problem. So now I want to talk a little bit about two solution techniques that we proposed in this work to solve this kind of bilevel optimization problem. And the first idea is, well, we have a bilevel optimization problem. What's the classical idea for that? You reformulate the bilevel optimization as a single level optimization problem using the KKT conditions of the problem. So what we are doing here is we are taking this second level and writing the KKT conditions of that. So first, let's analyze the difference between the two problems. So in the left side, we have the reformulation. In the right side, we have the same problem from the previous slide. So the objective function is the same because it was already a polyhedral function or a convex function. In this work, everything is polyhedral. The second part is the forecast. It's exactly the same. In the study cases, we will focus ourselves in linear forecast functions, although in other schemes we could have different things. And after that, we have the reformulation of the second level. So first, we have the primal feasibility constraints of the second level. Then we have the dual feasibility constraints. And finally, we have primal dual complementarity constraints. So the first two blocks of constraints, primal feasibility and dual feasibility, are easy to handle. Everybody knows that. But the thing that is a lot of work is dealing with the complementarity constraints. Dealing with the complementarity constraints require a lot of work, and there are a few techniques that people have been proposed in time to deal with those. So one of the main all the ideas are on these constraints, and I'm pointing out three classical ideas over here. One of them is using SOS1 type of constraints, in which you can have each part of the complementarity in a SOS constraint, and that will guarantee that one of those is 0 always. And how that's being done? That's done inside the solvers, inside the branch and bound procedure of the solvers. So the optimal solutions will guarantee that by definition of the solving process, that will be solved. The second method is called the big M method, in which you add binary variables and big M constants so that you can shut on and off some of these constraints. And that's a classical approach called Fortuny-Yamaha, which dates back from the 80s probably. And the third option is doing an NLP formulation, which people have done. And what's done in that point is that you take both of the pieces of the complementarity and you just do like in a textbook presentation of complementarity. You multiply both of them and say that they are equal 0. The problem with that, there are a few issues with that reformulation. The first of them is that problem is terrible for nonlinear programming solvers because that doesn't respect what people call a Mangasarian-Fromovich qualification constraints. And so what people do is, instead of saying that those two are equal 0, they say that the product of those two is less than epsilon. a small number so that regularity conditions are improved and the solvers can work better on that. And then people try to reduce iteratively the values of epsilon to do that. However, the nonlinear programming solvers do not guarantee optimal global optimality. So they only guarantee local optimality also, so different from the other two methods. Although the NLP formulation is much faster, it doesn't guarantee global optimality. One of the things that was used a lot in our project was this package that we developed, which is called bilevel jump. So for the ones who know what jump is, doesn't know who jump is a modeling language in Julia. So you can write your optimization problems, and those problems are passed directly to the solvers. So you don't have to build A matrices and C vectors and B vectors and so on and so forth. You just write that as you were in AMPL or GAMS. Bilevel jump in its hand, differently, uses all the jump syntax to formulate a bilevel optimization problem, and automatically he writes the problem using dualization techniques automatically, so that the KKT conditions are written automatically, and everything is passed to the solver in the form of any of those reformulations that I listed previously. So the good thing about that is that you don't have to keep rewriting duals and complementarity constraints of your problem. You just rewrite your problem and everything will be done automatically. So you want to add a new constraint, you just add to your formulation and everything will be straightforward. I just added a small example of a simple bilevel program so you guys can see the syntax of this thing. So you can add variables to either the lower or the upper level of your bilevel optimization problems. Then you can add objectives and constraints to the upper and to the lower problem. And this formulation is very simple. It's just what you would like to write in a paper of your problem. So you write that, and then when you hit optimize, it will reformulate the problem and solve the reformulated version of the problem. Now I will talk a little bit about the second technique that we propose to solve that problem. Because the KKT reformulation either leads to local optimal in the NLP formulation or leads to very difficult solving times, and which means very limited problems. We developed this heuristic method that is very interesting because it has very nice features on the computational aspect. So the heuristic method goes as follows. I will read to this math algorithm following our favorite figure of this slideshow. We first initialize the theta. The initialization could be as simple as, well, you start with the least squares estimate of your theta, and then you start from that and you optimize from that. So while your problem have not converged, you will follow the following loop. You can start forecasting. So given any theta that you started the problem with, you can do a forecast based on previous data. After you have the forecast, you send that to your optimization problem that solves a planning. That's a linear programming problem. And that returns you your planning vector. And you grab that planning vector and you pass that to the cost assessment function. So your final cost will be evaluated at this point. And after that, what you can do is, well, you get that cost and you can update your theta based on those costs that you have just evaluated, which closes the feedback loop. Oh, I forgot the orange box here in the training. The orange box should be here. And so this heuristic method just follows what the figure tells you to do. But the interesting part is that, well, this for loop here in T, which are the observations of the problem, is massively parallelizable. So you can parallelize that on all your observations. So you can solve all the problems separately because the only thing that is common to all of them is the theta that was decided previously. Second thing that is extremely efficient in this method is that all we are doing here is that we are solving linear optimization problems, and the only thing that changes in those problems is the right-hand side of those problems. If you're only changing right-hand sides of the problems, that's extremely powerful because you can exploit the dual simplex method. And after the first iteration of the problem, it will be just a few iterations to convert the simplex method again. So while the first run of the simplex method might take like 5,000 iterations to converge, although that can be like a few seconds, the following iterations usually are really, really fast because they can take like a dozen of simplex iterations. So they take less than milliseconds to be solved by off-the-shelf solvers like Cplex, Gurobi, or even Express. Now we want to take our problem and write the load forecast and reserve sizing problem based on the generic formulation that we have written. So the first thing that we do is we are showing the two levels over here, and we can see that here we are forecasting demands, up reserves and down reserves. And that is, well, the same thing as the forecasting in the other step. The other part is, once you have the forecasts, you pass those forecasts to this second level problem, which is the planning problem. So in this planning problem, we are taking the forecasts here, the demands and the reserves are right-hand sides of constraints in this problem. And from that, you have set points of generations and up and down reserves for each of your generators. Once you have that plan, which is detailed in form of set points and reserve allocations, you can plug that in your first level problem and evaluate what would happen if a different demand was realized at that point. So now you have your historical demand being realized. So now instead of a D hat, now we have the actual D inside of these problems. And the system must adapt within the bounds of the constraint. Here I'm just highlighting that the objective function is in part the cost generated by your plan, but in the other part in blue is the cost that happens due to adaptation of your problem in the final step. Here is just a review on what means what on this optimization problem. So both of the orange boxes, both in the upper level and the lower level, both of them represent the scheduling of power flow, either pre-scheduling or post-scheduling after uncertainty is observed. In blue here, we have the reserve scheduling. In green is generators bound because reserves must be within the set point generation and the physical limits of the problem of the generator. There are bounds on how much reserve each generator can provide, and there are also the operation bounds of the adaptation step. And in black here, in this last two blocks, is just guarantee that everything is positive. It's just extra bounds on physical limitations of variables and other basic rules. So now I would take that problem and I will do a bunch of case studies based on that problem. And all these case studies will be either based on a single bus system that we developed. It's like a 4-generation system with one demand in one single area. The areas or zones are just clustering of generators and buses, so to represent how the generators can respond inside of those. And the other 3 case systems are classical 24 bus, 118 bus, and 300 bus power systems with some modifications that are described in the paper. We changed a little bit of the demands and the power limits so that we can have more interesting results. And those are available on GitHub Online. And during most of our presentation, we will use this demand forecast function, which is a AR1 forecasting function. which is the same forecasting, which is the same stochastic model used to generate the demand data. So the actual demand data generated on this for these problems will be a AR1 process. And we will consider that we know that everything is an AR process. So we will forecast demands as an AR process as well. And the reserves in the first case study, they will be basically static. So they will just have a constant coefficient to estimate reserves, which don't mean exactly that the reserves are static, because in theory you can reapply the algorithm for each new data that comes to your system, so you can readapt that all the time. But for simplicity, in the first case studies, we will just assume that the reserve forecast is a constant function. Our first case study is in the small one bus power system. And what we did was, well, in this small power system, we varied the number of samples from 15 to 75. So we used all these numbers over there. And we did a bunch of runs of both the exact bilevel formulation of the KKT method solved with mixed integer nonlinear programming, actually mixed integer linear programming, and compare that with the heuristic algorithm. Blue line is the constant function, so is the identity function. So what we want to show here is that although the heuristic method sometimes is not perfectly estimating whatever is happening in the bilevel formulation, it is really, really close to what it should be. So what we want to show with that is that the heuristic method is reasonable, and because of that, we will use that in the next case studies. In the next figure, I wanted to show some insight on why those results were really good on that scatter plot. And the reason for that is that the cost function of the bilevel problem has a really, really nice shape. Although it's not convex, it's like quasi-convex functions that are really good for descent-like algorithms like Nelder-Mead that we are using in our heuristic. So the first two plots are the objective function as function of the reserves with fixed forecasts for demands. And the second ones are the cost functions for estimating the AR parameters of the load forecast, but with fixed reserves. Now, we want to do some case studies varying the sample size of the problem to see how things are converging and how results and how the optimal results are converging in this problem. So first, let's talk a little bit about the types of problem that we solved in this case. So we will solve basically 4 models for each power system. And the first of the models will be represented always in red, which is a least squares forecast for loads, while we have an exogenous demand forecast. In blue, we have a least squares forecast for load, but optimized reserves. And this optimization will be done with respect to the application cost function. Then in yellow, we have the opposite. We'll be optimizing loads, but with fixed reserves. And finally, in green, we will optimize everything. So in this first graph is just the cost function of the problems, varying with the size of the sample that we are using. Look that we can reach even more than 1,000 samples in the same problem because our heuristic is very efficient. But these results are just in-sample results. So they just show how the optimization problems did. And well, as expected, the green is always below all of them because they have more degrees of freedom, while the red, which doesn't have any degrees of freedom, is above all of them. And the other two are just in between. Now, I'm presenting the out-of-sample results of this training process. So here we have the lines representing the average values of I think, yeah, of 100 realizations of sample sizes. So for each sample size, say 600 samples, we generated 100 samples with size 600. And we trained the model for all of them, and then we evaluated the model in the same out-of-sample, huge sample of 10,000 samples. And we got those confidence intervals. So the confidence intervals are the 10% and 90% confidence interval. So we can see that even in out-of-sample, we are being able to extend our results, and the results, and we see that the green model that optimizes everything goes much better for reasonable sample sizes, while the red, which is the exogenous or and least squares estimation, everything is exogenous, done from outside, not taking into account the actual cost function of the problem, is always the worst, while the other two are just here in between. This figure in the right is just small sample sizes. And what we wanted to show that is that, well, the model is very good for large sample sizes, but for small sample sizes, the model has larger variation. So it might be more challenging to use this model with very reduced sample sizes. We don't have that much good solutions, which makes sense because of, well, all the estimation process, just like people have been done in machine learning for a while. The next two slides, so this one is the first of them, we'll talk about the convergence, not of the objective, I have a bad title over there, but of the parameters, and I'll say, I mean, the solutions of the estimation process. So here, I'm presenting the solution of the theta coefficients of the demand forecast. So the first thing that we see here is that the least squares estimate has a smaller confidence interval, and it's converging to the actual values. As I said in the paper, I didn't bring the values here, but the actual values is exactly like 0.7 and 0.9 over here, while the green and the yellow models, in which we are able to optimize the demand forecast based on the actual cost function of the problem, we are able to bias those forecasts. And with those biased forecasts, we got the good results from the previous slide. But anyway, the nice thing here is that we are showing that those coefficients are basically converging somewhere. Not as fast and not as steady as the least squares, but it's reaching reasonably stable results and that are biased. Here are the same results for the down reserves and up reserves. So the idea is the same here, to show where those parameters are going to, and they are steadily going to the same places. Second, here in this slide, I wanted to highlight the biased forecasts on our results. And in red, in this first histogram over here, you can see that the histogram is basically centered in 0, and it's symmetric. So this kind of yellowish color here is just the intersection of the two histograms. And this is telling us that, well, the actual forecast for the least squares is symmetric, just like we expected. And however, the forecasts for the fully optimized problem are significantly biased, as we can see here in the right, because its average is like over here, around -1, for instance. And in the right-hand side, we show the same information, but in a form of cumulative probability functions. So it's, again, the demand forecast error with respect to its probability. So again, we can see that the 0 is right over here for the least squares, which is in red, while the green one, everything is shifted to the left. This is yet another case study where we are doing the following. In this case study, we are assuming that the demand forecast, that the demand stochastic process, not the forecast, the demand stochastic process is heteroscedastic. So as you can see, now the variance of the residual of the stochastic process of those chunks are time varying with that ET function. And for simplicity, we consider that ET function to be also a autoregressive process. And this in the left is the solution, is the out-of-sample cost evaluation of the problem that optimizes the demands and the reserves based on that previous model where demands are a AR1 model, but the reserves are just a constant. In the right side, we changed the reserve forecast to be, instead of a constant, just like we had in the past, just the theta 0, we have now a theta 1 that depends on the ET. By having that exogenous variable, we can see that we can have much better results than we have in the kind of static reserve setting. So what we wanted to show here is that this methodology allows you to consider that. Second to final, this is the second to last example. We wanted to show how the demand forecast and the reserves vary with the deficit cost. It's very easy to see that the demand forecast is varying a lot with the deficit in the first few changes, but then it still changes but less abruptly. Slightly harder to see in this picture, but we can see very clearly in the blue one, at least, which are the reserve margins for the model that only optimizes reserves, is that when you increase deficit cost, you are increasing reserves of your power system. The red doesn't change because it's an exogenous static reserve. In the green, there are two things increasing. Both the range of the reserves are increasing and also the demands are increasing. So it's slightly harder to see that this range of reserves is larger now. And our last study is now, we'll pick all this very nice methodology that we developed and we test a lot on a small power system, and we will apply that to very large, well, not very large scale, but large scale power systems that are classic in literature. So here we apply the 3 of the models for the 24 bus, 118, and 300 bus power system. And we can see in this figure that the test is the out-of-sample cost and train is the in-sample cost. We can see that not only the in-sample cost improves with the different methodologies, but also the out-of-sample cost also improve with the different methodologies. So using the methodologies that can change more the forecasts can improve a lot the out-of-sample results. Well, and the cost of that is basically you're expending more time training your simulation. So, well, estimating least squares is, well, I said it's 0, but it's basically a negligible time to solve the least squares problem to estimate reserves, while we can see a much increased time to estimate the other models, which can reach to almost 1 hour to the 300 bus power system. But that pays off by having a meaningful decrease on the final out-of-sample cost of the system. So now in my last 2 minutes, the main conclusions of this work, which are, well, we are describing a new framework for optimizing jointly forecasts with the actual cost function of the problem. And we presented a heuristic that is capable of approximating the bilevel formulation. The heuristic is shown to work very well in large cases, both in performance and in cost results. And clearly the method outperformed the classical open loop framework in all those test cases. In the case of reserves and forecasts, we've shown that clearly optimal load forecasts are biased. we've shown that that bias has a lot to do with the deficit cost and with the reserves. So co-optimizing reserves and loads is very important. Finally, we've shown that these results are extending to large-scale power systems. So after these conclusions are just some references so that I can send the slides to you later and you can have their references easily over there. I don't have time to talk about here, but after you guys talk, we have a very recent results, which is a convergence proof showing that this model is converging to where it should be converging, which is the average of the, well, not the average, the expected value of the cost functions. We can talk a little bit about that if we have time later. The proof is really recent. We did it in the last 2 weeks. So now I'm finished. Thank you very much for your attention.